we say that these bases are mutually unbiased. And what we mean is that the projection of this onto this is exactly the same as the projection of this onto this onto this, etc. So that means that if you make a measurement here and you find out you have this mode here, it provides absolutely no information about what the state would be in this other basis, and vice versa. So how does the BB84 protocol extended to OAM work? So, the idea is that you have two people, Alice and Bob. Alice is trying to send information to Bob. Let's say she wants to send the string 13, 3, 2, 3, 15, etc. For each symbol, she randomly chooses either the Laguerre-Gauss basis or the angular basis. She sends this to Bob. Let's assume for right now that there are no transmission errors. Then Bob randomly chooses one of these bases. If after the whole transmission is over, Alice announces publicly what basis she uses, certainly not what number she sent. And then if Alice and Bob use different bases, Bob just throws this one away. If they use the same, he keeps it. So they end up with a string of identical numbers. Alice has a string of numbers, Bob has the same string of numbers. So you can do absolutely secure communication this way. It's called a one-time pad. Right. People who break ciphers do this if the encoding makes use of some prescribed algorithm. And then you say, well, if they're transmitting in English, the letter E comes up far more often than the other letter. So you find out which one came out the most often. It's probably E. And then I think it becomes even more sophisticated than that. If you ever saw the movie about the Enigma machine. But a one-time pad is believed to be inherently unbreakable. Okay, so we built one of these. We actually built this in Rochester, although Ebrahim right now is building something very similar here in Ottawa. So in our first example, well, Alice and Bob were sitting on two different ends of an optical table, and this free space channel is maybe this far. So Alice takes her laser beam, attenuates it very, very strongly, so that on the average you have fewer than one photon in each transmission. The spatial light modulator then encodes any OAM mode or any angular mode onto this beam. She transmits it over this free space channel. Then Bob has this horrendously difficult challenge. He receives one photon. Well, he guesses what basis set to use. Let's go back to this. Bob receives one photon. He can make only one measurement because it's one photon. He has to try to figure out which one of these it's in. And that's very, very difficult because you only get to make one measurement. And the intensity patterns here overlap one another. So if you get a click here, you don't know whether this is this. So our colleague, Miles Paget, found out a way to do sorting of OAM modes. And it's a very, very tricky, very clever design. He first constructed what I like to call the world's worst lens. A good lens makes a perfect image of an object. His lens is so bad that the image of a donut is a hot dog, to pursue a culinary analogy. So there's so much astigmatism here that the image of this looks like this. There is a branch cut, and you have to look at my arms. As the light propagates across the screen, it just opens up like this. Now, a phase variation around a donut, how in the world do you measure it? But a phase variation of a plane wave is just a wavefront tilt. So you put a lens and you see where it hits. And that was his design, and let's say it works very, very, very well. So we put it together. We put it together. Here was the system that we actually built. In this case here, we used a state space of 7 elements, not 26 as before. You ask why only 7? You probably think it's because our spatial light modulator wasn't good enough, but it wasn't that at all. It's that who in the world can afford 52 avalanche photodiodes? So it's just a matter of getting one single photon detector for each channel in the design. So we used a much smaller state space for this work. And well, the lead author here, some of you might guess what country he is from. It's not China. Okay, so this is some very famous Persian wall writing. So you digitize this, you send it over a free space channel. Once you've encoded this using the secret key, so somebody who intercepts the code has no idea what this is, but then at the other end you put it back together, and the received image is just as good as the one that you sent. I know this is very, very boring to look at a string of numbers, but the whole idea of QKD is to send a string of numbers from one place to another. So you're supposed to show people your data. In this type of experiment, this is the data. This is a string of numbers that we transmitted in a highly secure manner from Alice to Bob. We do crosstalk matrices. Well, ideally, what you get should be what you sent, but in reality, sometimes what you get is a little different from what you sent, but doesn't look bad. Maybe this is the best way to summarize this. A 7-letter alphabet, well, log base 2 of 7 is 2.8. So you could, in concept, be able to encode 2.8 bits per photon, and we got 2.1 bits per photon. And this was largely due to crosstalk, that you sent an OEM value of 3, but maybe it showed up in the OEM2 channel. And there are ways of quantifying the security. How much error can you tolerate and still produce a totally secure system? The way you look, well, there's many ways of looking at it. One is to say, if an eavesdropper ends up with more information than Bob, it's all over. But if the eavesdropper has less information than Bob, then there are classical protocols that you can implement to make the system more and more secure. I mean, it takes, you take the string and you make it half as long, but you can make it more secure by making it half as long. Okay, so what's going on in our laboratory now? So Alan Wilner, who maybe some of you know, he wrote this famous paper, terabit per second free space telecommunication using OEM states of light. I had published this paper here. We had a 10 hertz transmission rate. Alan and I said, hey, let's start working together. Let's combine your security with my high-speed communication. So we're building this system right now. And just telling you that maybe if you invite me back in the future, I will tell you about a high-speed, highly secure communication system. And we are out of time. So I'm just going to stop here. So thank you very much for your attention.
Thank you very much, Bob. So we have time for a few questions. Any questions? Yes, please.
So, fantastic talk. I really enjoyed it.
Thank you.
If you go to the error rate fields that you have it, so was 2.1, it means that essentially you're sending information in dimension 4.
Yeah,
Because, and
we had 7 channels, but only effectively 4.
4.
Yeah, something like that.
Effectively 4. Even half, close to half of the real space that you have it.
Yeah.
It's not so much.
I prefer to say we had 2.1 instead of 2.8, to say that we had 4 instead of 7, but that's how logarithms work, right? Experimentalists always want to take logarithms. It makes theory and experiment look closer. But anyway, agreed. Or you can plot the log of your of your data. It always agrees with theory then. Yeah, sorry.
When you say the free space limit, at this point, like, what is the prediction? How far can you actually transmit?
Okay, there are 2 limits. This is a very general. I take this as a very general question. I'll answer it as such. There are 2 main things you have to worry about. One is if your beam diffracts so much that the receiver only collects a small amount of the light, then your data rate goes down. If you go through how QKD works, it turns out that lost photons don't hurt the security. Lost photons do not hurt the security. You say, but what if the eavesdropper recorded that photon? Still not a problem, because if Alice sends a photon and Bob doesn't receive it, I mean, she knows that something went wrong, and that will not be included in the protocol. So first of all, there's diffraction, and it's actually not as much of a problem as you think. I mean, a dish of maybe a meter, I mean, Earth to space works. We can go through the numbers. For free space, it's atmospheric turbulence is the real problem. Atmospheric turbulence can put a random phase on your wavefront, and the random if you have an OAM of 2 and you add a random phase to it, it'll be a linear combination of maybe 1, 2, and 3. So some fraction of the time the light ends up in the wrong channel. With our colleagues in Erlangen, Ebrahim here in Ottawa is doing quantitative measurements to see how much of a problem that is. Preliminary answer is it's a problem, but there's something called adaptive optics, and adaptive optics is very, very good at correcting for these things. So a protocol would be to have 2 beams of light, your very weak signal beam, and a classical beam as a beacon or as a tracer. So this classical beam senses the wavefront distortions, and you either do feed forward or feed back and remove it. This works very, very well. So well that the U.S. government will not tell us how well it works. But they are the experts at looking down and looking up. And it's believed that this works very, very well. So we're prepared to implement that.
Any more questions?
Yep.
So in this free space application, what happens when the photons go through a media, let's say, amplification media, the photon goes through multiple
Goes through
stimulated photon.
amplification.
Amplification media. So it'll have.
You mean in concept? There was nothing. We're not doing this.
No.
But you said what would happen?
What would happen? Yeah. Can you preserve?
For the, I think so. This is in general or for QKD?
In general.
Yeah, so amplification preserves the wavefront, the phase front of the light. So that's why lasers work, I guess you could say. Or laser amplifiers. So the wavefront structure is preserved. Now, for the quantum application, there's something called the quantum theory of the amplifier. And we know that no amplifier can, no phase-independent amplifier can amplify without adding noise. So when you amplify a beam of light, you add noise to it. There are many ways to see this. The intuitive way is that whenever you have stimulated emission, you have the possibility of spontaneous emission. So the spontaneously emitted photon will enter the beam randomly, and that degrades the noise. And I think we all, good engineers, we talk dBs. It's the 3 dB noise limit. So no high gain, every high gain amplifier has at least 3 dB of noise penalty for using it. And then it's a systems issue. Nobody wants to add noise to their beam, but if amplifying it allows you to detect it when you otherwise couldn't detect it at all, maybe this 3 dB noise penalty is something that you're willing to accept. And these things are fun too, to study the noise properties of the amplification process. Yes?
Maybe this is a naive question, but in your implementation of the BB84 protocol, there is laser. There are no single photon sources.
Yeah.
So how can we be sure that this protocol is still
Okay.
quantum-based
Okay,
protocol?
that's still another story. Okay, so in the best of all worlds, you take a single photon source, and each transmission is with a single photon. There's a huge amount of work going on developing single photon sources, but they are still not ready for implementation. So so you say, well, why don't I just use highly attenuated laser light? The trouble is, you say, well, I'll attenuate my laser light so it's 1 photon per transmission. But if there's 1 photon per transmission on the average, occasionally there will be none. Well, you've lost data rate, but you haven't lost security. But occasionally they will send 2. And then there's always a chance that the eavesdropper will steal one of those 2 photons, and you'd never know it. Because Alice sent a packet which she thought had 1 photon but has 2. Bob receives a photon, but the eavesdropper has a photon. So the first thing you can do is send on the average 0.1 photon per transmission, and then there's a really negligible chance that you will send 2 of them. The amount of information that the eavesdropper could acquire is sufficiently small that classical privacy amplification can ensure that that it is absolutely secure. But that's not the whole story. There's a professor at Toronto, Professor Lowe, and I can't pronounce his first name to my embarrassment. Professor Lowe at the University of Toronto has a protocol that's called decoy states. And the idea is that instead of always sending at the same level, you send at 2 different levels, a weak level and a strong level. But the eavesdropper doesn't know if it's a strong level, a strong signal. She doesn't know if it's a strong signal, and of course she was able to steal a photon from it, or if it was a very weak signal and in a probabilistically unlikely event, she happened to get the photon. And if you go through the analysis, this messes up the whole thing. So something as simple as just randomly choosing between strong and weak sources and then doing the analysis correctly allows you to send on the average maybe 1 photon per pulse and still maintain security.
I enjoyed the talk.
Well, thank you.
It was very nice talk. I have a general question. It's the following. So for decades now, for decades, I would say, it is expected that perhaps using nonlinear optics, photonics might one day replace electronics, to do all optical processing.
Yeah.
For decades now, people have been expecting this. I was
Before some of you were born.
so,
Huge I mean, I think it was Peter Knight talking about that last week. Yeah, so I mean, this was a huge thing in the 1980s. All optical computing, yeah. It was Alex Gate, I think, who said that.
so I was wondering, what is the ultimate goal? In other words, first of all, what is your opinion about this? If photonics using nonlinear optics might, for optoelectronic applications, if it might ever replace, electronics for all optical processing,
Okay.
or if it would rather be used for just transmitting information.
Oh.
And what is the more in other words, what if we rephrase the question, what is the ultimate target? How fast, what is the loss operation, the loss performance for, let's say, the best nonlinear optical structure, optical material that you can imagine, and if then this could be used for replacing electronics?
Okay. So, perfect question. I'll point out I'm not a systems engineer. I'm only barely an engineer. I am a professor of ECS at this university, but not a systems engineer. So I think the general answer is that it seems very unlikely that photonics will replace electronics for general purpose information processing. But it can be very useful for specific applications, optical interconnects being an obvious one. At least in air, light beams pass through one another, so you don't have this tangle of wires, a rat's nest at the backplane of your computer. So optical interconnects would be one example, and even some all-optical switching. All-optical switching, you can imagine that this will be for real. Optics can be very, very fast, and well, you certainly want to transmit optically. So why take the optical signal, turn it into electronic signal, process the electronics, and turn it back to optical? So there's be a huge advantage in terms of even energy consumption. Green photonics. In the developed world, it's something horrendous. 10% of our energy goes to running data centers, or it's projected that it will be up to 10%. So I tell people that they should use, they should encode in orbital angular momentum. I can encode many bits per photon. Right? So if properly implemented, and believe me, I don't know how to properly implement it. I mean, you could imagine a huge energy saving in doing your transfer of information in a much more efficient way. So those are just a few ideas. Clearly, photonics is for real. Our graduates get jobs. So, I mean, it's not just a professor saying, oh, yeah, you should do what I do. I think that if you look financially, a huge part of photonics is building building LED displays and building lighting for automobiles, LED lighting, and LED for the home. You say, well, that's not real science. The Nobel Committee thought otherwise, right? So let's recognize that maybe that is real science. So I mean, I love the nonlinear photonics, but there are always going to be it's a much more huge market to build lighting than it will be to build ultra-fast optical switches. So just a few thoughts to share.
Is there any more questions? Okay, no question. We thank the first point.
Okay. Well, thank you for the invitation again. Thank you.